Okay, right, thanks David. So yes, this is a second lecture out of 2 here. Got about halfway through the slides last week, but the second half is a little more dense than the first half. So we might be here till a little after 6 o'clock. Sorry about that. So the last thing we were talking about last week was classification. Just going back a couple of slides, we were talking about nearest neighbor classifiers like this, where we have a bunch of training data and we assign a new input vector x there to one of the classes depending on which training samples it falls nearest to. So in any system like that is based on training data, a problem arises known as overfitting. And the corollary of overfitting is how good or bad the system's generalization is. I'll just explain what that means. So one way that the data is often handled is you're given a big load of training data and you split it into training and test sets. So you do the training with the training set, surprise, and then you evaluate the performance on the test data that you put to one side originally. And the problem with overfitting is that any system will naturally perform better on the training data than on test data, because that's what it's been trained with. Even if both are samples from the same probability distribution, doesn't matter how good a sample they are, you will always potentially get this overfitting problem. And you'll get it worse if there's less training data, if there's noise in the training data, if you try to learn too many parameters from the training data. For example, if you have models that are too complex or complex decision boundaries in a nearest neighbor classifier. Okay, so here's an example, very simple conceptual example of overfitting. We're going to fit this nth order polynomial. This comes from Chris Bishop's book here, by the way, Pattern Recognition and Machine Learning, which is a very good book, but it's pretty mathematical. Nevertheless, I'd advise you to have a look at it if you can. So we've got an mth order, big mth order polynomial here with m plus 1 parameters, a0 up to am. And we're going to fit that to these n data points, x1, y1 to xn, yn. And when we do that fitting, we get an error here. So for each of those data points, how far is it from the polynomial that we're fitting to it? Squared error, summed over all the points, take the square root of the sum. That's RMS. RMS is root mean square, in case you haven't seen that. So the data that we're going to try and fit to are these blue circles here, and they come from this underlying green sine wave here, but we don't know that. All we know is the blue circles, the data. So here's a sine wave plus some Gaussian noise to give us our data points yi. So if we try to fit a 0th order polynomial, that's just a constant, to these data points, here it is, red line. Not a very good fit. First order, that's a linear function. We try to fit a linear, the best linear fit to all these points. And it looks like that. Still rather a long way from the data points in many places. Here's a cubic polynomial now, m is now 3, and that is a much better fit to these data points. Still not great, but not bad. So if we keep going and increasing the order of the polynomial, do things get better? And the answer is, up to a point, yes. But if we go too far, here's a 9th order polynomial now, which can exactly fit these 10 data points. Great. So we've exactly fitted the data. Should we be happy about that? Probably not. Because although we've got 0 error on the training data now, you can see that an arbitrary new point is unlikely to be well approximated by this data, this approximation. So we've overfitted that function to the noise in the data. If you look at this, the function is going all over the place just to try and accommodate the noise in the data. So approximation is likely to be very poor for new test data, and that is the way that's usually rephrased, is that overfitted solutions have poor generalization ability. So here's the error as we increase the order of the polynomial. When we hit the magic number 9, with which you can exactly fit 10 data points, the error necessarily becomes 0, but the error on novel training data goes through the roof. Okay. The difference between these two curves illustrates the fact that you will always do worse on your test data than on your training data. Okay. So back to this example from last week. We had a linear boundary separating these two classes of salmon and sea bass. And of course it gets some of these points wrong. Some of the points are on the wrong side of the boundary, but you might guess that that is probably better than this overfitted boundary here, which exactly fits all the training data. But if you have a novel input point where this question mark is here, chances are it could be wrong, very likely to be wrong. So, how can you reduce or avoid overfitting? Well, there are a number of things you can do. One is to choose the model complex enough, but not too complex. That's a principle known more generally as Occam's razor that you've probably heard of. An approach to doing this is a thing called k-fold cross-validation, where given a big bunch of training data, you partition it randomly into big K sets, use all but one of them for training and use the other one for testing, and then rotate through all these K partitions of the data. In an extreme case where there are K data points, so each of these sets is one point, this is called leave one out cross-validation. Okay, so that's enough on that. I want to say a couple of words about the application context in which pattern recognition systems operate and how much of a difference it makes to what you can say about how well they're going to do, using the example of face processing. So detection versus verification versus recognition, this all tends to be lumped in as pattern recognition. It's all the same thing, but it's not. So in face detection, what you're trying to do is determine whether an input pattern, a part of an image, is a face or not. In verification, what you're trying to do is that face person A or is it not, presumably some other person. In face recognition, you have a database of n stored patterns and you're trying to find the most similar one. So whose face is the input face is the question that's being asked. And the problems are quite different in each case. And the failure to understand that leads to these bad outcomes down here. So, first of all, face detection, our input may be a face or not a face, and the output, if everything goes well, it will say face when the input's a face, and it will say non-face when the input's not a face. When things go wrong, you can have either false positives where the system says there's a face but there isn't, or a false negative where you miss a face and the system says there isn't one. From these different types of error come performance indices known as precision and recall. And you'll see precision and recall used in a wider context than this for things like search, retrieval, and so on. But in the case of face detection, these are the definitions of those. For verification, where you're given a face and asked, is the input face the same face as this specified face? There are, again, the truth table looks pretty much the same. The errors are false reject or false accept, and you can categorize the systems by how well they do with respect to these errors. So false accept is when some other person is accepted as the wrong person is accepted as the person who it should be. False reject is when the person who's in the input is not accepted, although they should have been. So bear in mind this false accept rate is a fairly basic parameter. It's also the most important one for security, because if you let the wrong person into your building or whatever, then you've got bad implications for security. The balance between false accept and false reject tends to depend on a threshold. If you set the sensitivity of your detector and say, well, if the input face is this similar or more to my stored photo in the database, then we'll count it as a positive verification, otherwise negative. And as the sensitivity of your detector here, the threshold varies, so the false accept rate will fall and the false reject rate will rise. Where they cross is a thing called the equal error rate, for obvious reasons, and that tends to be used to characterize, to describe how good face verification systems are. If you plot false accept and false reject rates against each other, you get a thing called receiver operating characteristic. Funny name, comes from back in the days of old school signal detection. Anyway, where it gets interesting is where you're trying to do recognition, where instead of one-to-one matching, like in a verification scenario, you're trying to match one input face against n faces in the database. And the question being asked is, which of those faces is this, or is it none of them? So now the truth table here is a bit more complicated, and there are more ways in which it can go wrong. Principal among them are the false accept rate. Now I've put a suffix n there to indicate that it's with an n person database. And this is the probability that some unregistered person gets recognized as any of the n registered people. And you can state that in terms of the false accept rate from a single one-to-one verification like this. It depends here on the number of people in the database. False reject rate similarly is the probability that a registered person isn't recognized as one of the n registered people. Again, you can express that in terms of the similar parameters for a one-to-one matching system like this. This is a new one. This is where some registered person gets misrecognized as one of the other registered people. And again, in terms of the false accept rate from a verification system, it looks like this. And the implications of having this n now appearing are profound. So here are some numbers. So if we have a verification system with a 0.1% false accept and false reject rate, try and use that same system for recognition, what happens? Well, the false accept rate goes up with the number of people registered in the database. So if you've got 100 people registered in the database, the false accept rate climbs to just under 10%, which may or may not be good enough depending on your application. Put 1,000 people in the database, 63-point-something% false accept. You've got 10,000 people in the database, false accept rate is 99.9%, and basically you have no chance in this situation. So if you're computing distances from all input faces to all registered faces, also increasing the number of faces in the input is equivalent to increasing the number of faces in the database in terms of the number of false matches that it's going to generate. So, although verification, for example, at passport control at the airport or whatever, can work well with this false accept, false reject rate, you've got no chance of spotting people, for example, at an airport with thousands of people passing through, because the system gets swamped with false positives. The alarm's going off all the time. So this was made painfully clear after terrorist attacks in 2001 in the US, where people panicked and installed face recognition systems in airports all over the US and everywhere else. And they were hooked up to CCTV cameras in towns and so on. And the database was an FBI watch list, a load of pictures of bad guys. And the idea was to try and intercept terrorists or whatever at the airport. And the task being impossible, these systems didn't work well. And it was impossible because there were too many people in the database and far too many people passing through the airport for the conditions to be good for a system that was feasible at the time. This badly damaged the reputation of the technology and airport security, because when the alarm's going off all the time, you just think, turn it off and basically ignore it. Led to political shock waves which still reverberate today. The lesson is that you need to restrict both the number of people registered and the number of people in the input as far as possible, as well as using invariant and robust matching methods. Now we're seeing significant progress on face recognition, such as in Facebook tagging and so on, where there's some ID information available. You can restrict the number of people likely to be in photographs, etc. So, now onto the final bit of the course, which is machine learning. Some broad definitions. Basically, there are two types of machine learning, supervised and unsupervised. In supervised learning, or learning with a teacher, you have labeled training data. And that's used for training KNN classifiers, for example, parametric classifiers. LDA that we looked at last week is a simple example. A less simple example is support vector machines, which we'll have a look at later today. Unsupervised learning, there's no labels. The training data is unlabeled. You're just trying to find, for example, clusters in it. Estimate number of classes, parameters of class models. A simple example of this is principal components analysis that we looked at last time. And a less simple example is the EM algorithm that we'll look at this time. So mixture models are a standard way of describing clusters in data. So we're trying to find structure in unlabeled data here. This is unsupervised learning. It's unsupervised, except you may know the number of clusters, or you may estimate them. It's natural to model data like this. If you look at this, you think, well, it looks like there's two classes there. Because we're rather good at doing that kind of judgment. But mathematically, it's natural to model this data as a mixture model with one component per class. So this could be modeled, you would think, as a two-component mixture. So now I'm going to look at this k-means clustering algorithm. So we're given n data points, here they are, and a fixed number of classes, which is less than the number of points. And we're going to try to find the set of class prototypes, class means, if you will, and the assignment of each data point to one of those classes, which are described by this variable, which is a 1 if the nth point belongs to the kth class, and it's a 0 otherwise. And we need to find those class means and the assignments of points to clusters in such a way as to minimize this distortion measure here, which is the squared distance between each point and the class that it's assigned to, summed over all the points. Okay, so there's a recap of what we're trying to minimize. And the way the algorithm works is first we initialize the class means randomly. So there are k of them, choose them randomly. Then there are two steps, which I've called E and M because of the analogy with the EM algorithm, which you'll see afterwards. So the E step, we try to minimize this error with respect to the class assignments. So assigning which point is going to belong to which class, without moving the class means around. Then the M step, keep the assignments the same, but move the class means around. Keep doing this until nothing changes at some iteration. There's a recap of the error thing we're trying to minimize again. So the E step involves simply assigning each of your input vectors to the nearest class mean. Easy enough. The M step involves recomputing the class means as these things, which are the means of the data points assigned to each class at the previous step. In pictures, which makes it a bit easier to understand, we start off randomly assigning these class prototypes, the blue X and the red X up here. I've deliberately, or whoever wrote this, Chris Bishop, whoever made this figure, chose them deliberately badly. So at the first E step, we're going to assign each of these points that's closer to the blue X to the blue class, and points closer to the red X get assigned to the red class. And they're colored accordingly. Then the first M step moves the red X and the blue X to the means of these colored points. There's the blue X there and there's the red X up there. Then we repeat the E step, assigning each point to the nearest class mean. Repeat the M step, repeat the E step, etc., etc. And in about 4 iterations, nothing's going to change anymore, and the thing's converged to this result. You see the error falling at each of these steps. Okay, Gaussian mixture models attempt to generalize this a little bit more, where we're going to model a probability density from which our data samples are presumably drawn as a mixture of k Gaussian densities. So here are this big N is a normal or Gaussian density with a mean of mu k and a covariance of sigma k, which is a matrix. And the coefficients, these are constants, well, not constants because they change, but they're constants at each stage. Pi k these are the so-called mixture coefficients here. How much of each of these component densities is in the total one. So you can interpret these mixture coefficients as prior probabilities of each class. And if you do that, then the posteriors, that's the probability of some data x coming from class k, is this thing. And if you look at this is a mixture coefficient of the kth class times the Gaussian density for that class, divided by the sum of all of those over all the classes. In pictures, it looks like this. The red line here is the mixture density, and the component, it's made from these 3 component blue Gaussians in 1 dimension. In 2 dimensions, here's the same data. If you try to model this with a single Gaussian, it looks, well, the contours on it look something like this. If you try and model it with 2 components in the density, it looks like that, which you could probably intuit is likely to be much better. Here's a 3-class mixture in 2 dimensions. There's some contours of the 3 components. That's the sum of them, weighted sum of them, and here's your 3 densities over on the right. So what we do in order to estimate class means and covariances is we introduce these latent variables that control which class was responsible for generating the nth data point. So these are called responsibilities. And then these gamma parameters express probabilistically as a probability the probability that the nth data point came from the kth class. Okay, so that thing here is just the same, this prior class, the posterior probability, that the datum X came from class K. Okay. So much like the k-means clustering algorithm, we estimate the class means mu k and the covariances, and we also need now to estimate these mixture coefficients as well, using a thing called the expectation maximization algorithm. EM is more general than this, but it's usually used to estimate parameters of Gaussian mixture models. And it looks like this. What we're trying to maximize now, we had an error minimization with the k-means classifier. Now we're trying to maximize something, it's equivalent, but we're trying to maximize the log of likelihood. This probability here is the likelihood, so-called likelihood, which is the conditional probability that all the data, this capital X here means the whole data set. We're trying to maximize the probability of that whole data set conditioned on the set of class mixture weights, class means and class covariances. And the way that the algorithm works, first you randomly initialize all your parameters, mixture coefficients, class means and class covariances. Then the E step, we evaluate the responsibilities. These are the probabilities that each point was generated from each of the classes. Evaluate those based on the current parameters. That means the current centroid or mean and covariance of each class. And then at the M step, we update the parameters without changing the responsibilities. And then we go back and keep doing this again until it converges. The M step parameter updates look like this. The class means, the new version of the class mean gets updated as this thing, which you can see is a weighted mean of all the data points assigned to that class. Class covariance gets updated as a sample covariance of the points assigned to the kth class. And that's just been updated itself up here. And then finally, the mixture coefficients get updated as these are the means of these probabilities. Okay, again in pictures, using the same data. Now instead of just a centroid at each class, we've got a Gaussian distribution which starts off being circular. We start with the covariances being symmetrical. So the first E step, we assign each point not to one or the other classes, but probabilistically. We have a probability that it came from the blue class and a probability that it came from the red class. And you can see the colors kind of vary. So at the first M step, then we're going to recompute the mean and the covariance of each of these classes based on the mean and covariance, as the sample mean and covariance of each of these sets of points. Again, keep going, and the system converges to something that looks like this. Here's a dynamic example from the, this is from the Wikipedia page for the EM algorithm. You can see from a badly chosen original, each of these classes slowly converges to a fairly reasonable estimate. And you can see that the covariance and the mean both change together. Okay, so that's EM. EM requires more computation than a simple k-means clustering, as you might imagine, because you've got to evaluate all these means and covariances. and it requires more iterations usually to converge, but the results are better for classes with different or non-spherical distributions. So if you have classes with elongated distributions, then EM is going to work better usually. You can sometimes set the initial parameters for EM using k-means clustering, which then speeds up the convergence of the EM algorithm. They can both, k-means and EM, can both get stuck in local minima, and you can't guarantee to find a global optimum. It depends on your initial conditions, so it's always good to get good initial conditions. EM can suffer from a singularity, that's numerical instability, if a data point happens to lie exactly at one of the class means. EM is more general than this actually. There's and more difficult. There's a more difficult framework in which you can conceptualize EM beyond this, but that's beyond the scope of this course. Support vector machines, moving on. These were the biggest development in pattern recognition until deep learning came along a few years ago, or many years ago if you think Fukushima Sensei invented it, which is probably a fair attribution. So support vector machines were invented by a Russian guy, Vladimir Vapnik, who's now in the UK, at least I think he's still in the UK. And the soft margin support vector machine stuff comes from about 1995, so it's 20-ish years old. Applied to many supervised learning classification problems, and it tackles some problems with nearest neighbour classifiers, such as including overfitting, computation, and nonlinear decision boundaries. There's loads of software available to do it. libsvm is the main one. Pretty much everything else uses libsvm. So you can easily get hold of software to do the stuff for you. So what we're trying to do with the support vector machine is we're trying to maximize what's known as the margin between two linearly separable classes. Here are two linearly separable classes. Here are three lines, hyperplanes, that both split these classes accurately. But they have different generalization performance in that you don't need to have a point very far different from these before it'll get misclassified by one of these black boundaries. The best generalization performance comes from using the hyperplane that has the largest margin, and the margin is the separation between the two classes, the minimum separation between the two classes. You can see over here that this margin is actually determined by very few of the data points. It's actually only determined in this case by 1, 2, 3 data points. And we'll come back to that. So, assuming classifier outputs are -1 and 1 for the two classes, our hyperplane is going to look something like this, where we've got an inner product of some weight vector with the input data vector and a bias weight W0. Because the scaling of these things is arbitrary, you can choose to set this sum to plus and minus 1 at the two margins. So at this margin hyperplane here, we have this thing equal to -1. It's going to be 0 at the maximum margin hyperplane. It's going to be +1 over at this hyperplane on the other margin. Okay. Maximizing that margin turns out to be equivalent to minimizing this thing, which is just the squared, half the squared length of the weight vector, subject to these constraints. And there's one of these constraints for each data point I. And all these things must be greater than or equal to 1 for each I. Turns out this is a quadratic minimization. It has a unique global solution. And only the constraints for which this thing is exactly 1 are active. Here the constraints are greater than or equal to 1. only those for which it's exactly 1 are active, and those are the so-called support vectors, which are the points on the margin boundaries. In that previous example here, there were only 3 of them, 1, 2, 3. Okay, and this makes the computation considerably easier. Details of the derivation, see these texts, so I'm not going to bother going through the whole thing. That's fine if the data are linearly separable, if you can separate the 2 classes with a straight line. So what happens if you can't? One way of doing it is to introduce slack, so-called slack variables that relax the constraints and allow some wrongly classified points. And hence the so-called soft margin SVM is what that is. Another thing you can do is you can map your data into a high-dimensional space in which they are more likely to be linearly separable, and as can be proven. But to avoid the increased amount of computation that's usually associated with high-dimensional spaces, you can do a thing called kernel trick, which avoids computing inner products in this high-dimensional space by replacing inner products with this so-called kernel function. This is known as a kernel trick, or you can do both. And just to pictorialize those, this is an illustration of mapping this linearly inseparable space into a high-dimensional space in which the data is linearly separable. Points on the margin here correspond to points on the margin back here. Okay. There are several kernel functions that you can use. A popular choice is the Gaussian, which gives you a so-called radial basis function kernel. Here's an example with synthetic data from 2 classes, blue class and red class. Decision boundary is this thick black line here, which actually goes off the picture and back round up here. And the support vectors are these ones with green circles around them. So this guy and this guy, and this guy and this guy and this guy and this guy. Okay. Here's an example of a soft margin support vector machine, again with the Gaussian kernel. Here's the boundary, the decision boundary between blue class and red class. In fact, I think it kind of looks like there are 3 classes in there. And some of these points are misclassified, as you can see. So anyway, I'm not going to say any more about support vector machines. We'll move straight on to neural networks. And with the advent or the resurgence of deep learning in the last few years, neural networks have become popular again for the 3rd time. Actually, this is the 3rd time they've been all the rage. These are loosely based on the architecture of nerve cells or neurons, hence they're called neural networks. A simple neuron model known as the perceptron is a linear combination of the inputs followed by some kind of non-linearity. So again, there's our input vector x, inner product with some vector of weights w, add some bias term w0, and put the whole thing through a non-linearity, this function f here. So here's a non-linearity. Originally these were step functions, but they're not differentiable, which leads to problems. So continuous or differentiable functions have advantages here. Here's your input vector from x1 to xd, so it's a d-dimensional space. And here are the corresponding weights, w1 to wd. You can represent this bias term w0 as a weight in this vector by having a kind of dummy input which is always a 1 value. The weighted sum at this point is known as the activation of the unit before it goes into the non-linearity, and we'll come back to activations a bit later. Okay. So a single layer perceptron, which is literally just this thing, can implement a linear decision boundary. It's for obvious reasons. The output will be negative in this shaded region here, positive in this region up here. Here's your weight vector. The decision boundary is perpendicular to the weight vector. And a single layer perceptron can solve linearly separable problems like AND or. Here's an AND gate, inputs 0 or 1, 0 or 1, and the output should be a 1 only when both the inputs are 1. So a decision boundary down here will do just fine. Here's an OR gate. Again, the output should be 0 only when both the inputs are 0. So this decision boundary is great. Exclusive OR, you can't do it with a single layer perceptron for reasons which will be obvious. You really need these two boundaries and then some way of combining the two. So you can show that a 3-layer perceptron is enough to implement an arbitrarily complex decision boundary in your input space. So in theory, you only need 3 layers. You can do everything with 3 layers. In practice, nobody does for various reasons. But in theory, here's your input layer. Input vector comes in here. Input layer here computes hyperplanes in the input space, as we just saw with the single layer perceptron. Then we have this layer functions as an AND, effectively computing regions bounded by the hyperplanes that were computed back here. And then a further layer can take a union of these regions. And so long as you've got enough units, this combination of regions here can be as complicated as you like. So this network can realize any, however complicated, decision surface. So how do you teach a network like this? There's a thing called the delta rule, which is the rule that's pretty much universally used to teach these things. If a training vector is misclassified, we need to update the weight vector. That's how it works. So here's a system with weight vector W. Decision boundary is perpendicular to W. And here are some samples from class B and samples from class A. In this situation, it's working fine. So nothing happens. When we have a new training vector that gets misclassified, then we want to shift this boundary. So here's a new training vector, which is from class A, but it gets classified as class B by the existing boundary. And the way to fix that is to move the weight vector from there round here by adding this delta W term here. That shifts the decision boundary round to this dotted boundary here, and that will now classify this point correctly as well as all the others. Okay. And this weight update that we added here to the weight vector to get the thing to behave properly is some constant times delta, which is the error between the desired output and the actual output, and the input x. So that's why the reason this is called the delta rule is because it's something times delta times x, where delta is the error. Okay. So how do you train a multi-layer perceptron? If it's got differentiable nonlinearities, that makes things easy because you can propagate these errors from the output layer back through the network and change all the weights in such a way that they will reduce the error at the output. So here's the error at the output. A desired output vector is t, actual output vector is y. The squared difference between the two is this thing, and it's a function of all the weights in the network. Now we define a thing called the sensitivity of the ith unit as delta I. I've deliberately chosen delta for this for reasons which will become obvious, and that is the partial derivative of the error with respect to this AI thing, which is the activation of the ith unit, which we spoke about back here. That's the signal in this unit before it goes through the nonlinearity. Okay, so this is the derivative, or minus the derivative, partial derivative of the error with respect to the activation of the ith unit. Okay, so that's known as the sensitivity of the ith unit. And for an output unit, a unit in the output layer, the sensitivity is going to be, this is simply the delta of the output, that particular unit's output, and this is the derivative of the nonlinearity at the activation value AK. Okay, fine. That will then give you a thing called the generalized delta rule, because we've now got these nonlinearities in as well. Gives you the weight update as this thing. Again, it looks like the delta rule, something times delta times the input. And it turns out to be this. So something times the derivative of the activation of that unit times the error at the output of that unit times the input. Okay. So X here is the input vector to all units in that layer. They all have the same input vector. So what about the sensitivities of units in layers deeper than the output layer? You can calculate them by the chain rule, which is, you know, if you're trying to get a partial derivative of something with respect to something else, and there are intermediate variables on which they depend. So the sensitivity of some unit j in the interior of the network is defined as this thing. Again, Aj is the activation of the that unit. This thing is the derivative of the jth unit's nonlinearity at the activation value, and this is a weighted sum of the sensitivities of the units in the following layer, the layer nearest to the output. Okay, and this is where the term backpropagation comes from. This is known as backpropagation learning because it propagates the errors back from the output through the network. Okay, generalized delta rule gives the weight update for this unit j in some interior layer as, again, it's something times delta times the input x to that layer, constant alpha, derivative of the nonlinearity at the activation of that unit, times this weighted sum of the sensitivities of the units in the subsequent layer, times the input vector. Okay. So when people say neural network, generally what they usually mean, or even these days when people say AI, because it's recently become to mean almost the same thing, they usually mean something like a multi-layer perceptron trained with backpropagation. Okay. Here's that backpropagation in pictures. Here's the kth unit in this layer, and here's the jth unit in the preceding layer. K here is the output layer, so this is the error in the output of the kth unit, and here is the sensitivities of the units in the kth layer. They all get reflected back via these weights that join the two layers. That's these here. Take the weighted sum of the sensitivities of those units times the derivative of the activation at this unit, multiplied by the input, and that gives you your weight update vector for this unit. That's the weights going into that unit there. Okay. So, deep learning, what's it all about? Well, image and speech recognition, data mining, all these kinds of applications, some usually with labeled data, but sometimes not. This is an extremely active research area. In fact, it's probably the most active research area in computer science or engineering these days. Google and Facebook, Microsoft Research, etc., are pouring huge amounts of time and money into this. Deep convolutional neural networks are the flavor of the month here. They're called convolutional because essentially what each unit's doing is a convolution between the input and the weight vector. Weights are repeated, that's to say shared across multiple units in a layer. So the weight vector of this unit and the weight vector of this unit may be the same. That makes the shift invariant, which is useful for things like detecting the same object at any position in the image. And there are multiple trainable convolution hidden layers, hence deep, meaning many layers. There are usually some other operations as well, normalization and local averaging, etc. Okay, so training is usually by stochastic gradient descent. It needs a very large volume of training data. That's the downside of deep learning. Usually uses GPUs, which are the old graphics card, what used to be the graphics card in your PC. Particular manufacturers like NVIDIA have anticipated, they saw this coming and turned their video cards, their GPUs, into machines that are ideally suited to do this kind of thing. Previously, you had a bunch of processors which were good when they were assigned to, each one assigned to a small region of an image. Now you can assign them to a small number of units in a network that you're trying to train. A thing called dropout means that you randomly don't update particular weights on some iteration, and that tends to protect against overfitting. So here's a schematic of one of the earlier deep learning networks. Supervision is usually known as AlexNet because this guy's first name is Alex. This is about 6 years old now. It had 7 trainable layers and 3 layers doing other stuff. Took about a week to train by stochastic gradient descent on 2 NVIDIA GPU cards. So here it is. There are the input is the size of an image. Output is usually for something like image object recognition or classification. It's going to be the number of classes that you wish to have in your to identify objects as. So this was NIPS, which is Neural Information Processing Systems Conference in 2012. This was announced. A couple of years later, it had moved on to GoogleNet, designed by guess who, and they used a bunch of these, their so-called inception modules. You can see there's a kind of repeated modular structure to this thing. This had 22 trainable layers. The blue ones are the trainable convolution layers. The red bits are layers that do other things like local averaging or taking local maxima. The green ones are normalization and so on. This network had a couple of additional side branches. One of the problems with deep networks is that by the time you propagate the error from the output back to some deep layer in the network, the error signal has got so small that the training becomes very slow for the earlier layers in the network. So what they did was they had these couple of temporary outputs down here, and first they trained the network up to here with this side branch here to ensure that they got efficient, reasonable representations at this kind of stage here. Then they used this output and trained the network down to here, and then they finally trained the whole thing up. Okay, so that was 2014. Microsoft Research came up with a thing called residual learning in 2015. This network had 152 layers. And instead of learning a mapping h of x, whatever that might be, the idea was that you had this little loop here around your weight layer, and you learned the difference between that and your desired mapping. So instead of learning this h of x, learn the difference, or so-called residual mapping, between the desired mapping and this identity mapping. The reason for that is that quite often these are rather close. So rather than learning a whole new mapping, it's easier to learn a smaller difference between these things. So you initialize training from identity rather than from zero. If your desired mapping isn't too far from the identity, which usually it isn't, then this is much more efficient. Uses ReLUs are rectified linear units. This is a type of, just going back to here, rectified linear is a kind of straight line on the negative axis, and then a diagonal linear section up there. So the non-linearity is all at the origin. These are obviously very easy to compute. Okay, so that was these guys. This guy was at Microsoft Research. Is now at Facebook. Facebook seem to be doing the big noise work these days. The most recent of these family of networks is a so-called dense net, or densely connected convolutional network, from January this year. Has about 100 or over 100 layers, contains 3 or 4 of these blocks within which all layers are interconnected like this. So instead of just having one connection from the layer before and one connection to the next layer, you have connections from every layer, forward connections, that is, between all pairs of layers in each of these blocks. And that has a number of computational benefits. One of them is that you can propagate the error from the output back to earlier layers much more easily, because it doesn't have to go through so many layers. So it makes training faster and simpler. The error on this data set is about half the error of ResNet from 3 years to 2 years previously. Okay, so this was January this year. Looking at the history of deep learning on object detection and recognition, there was a thing called the ImageNet Large-Scale Visual Recognition Challenge. It ran until last year, from 2012 to last year. And deep learning networks have totally dominated it in the last few years. Back the first time a deep learning network entered, it was back in 2012. This is for a 1,000 class object recognition problem. Top 5 error rate, meaning that if your answer comes within the top 5, then it's deemed to be correct. So top 5 error rate back in 2012 was 16.4%, and that was much less. That was, I think, half or so of the previous best. In that competition, there was only one convolutional neural network entry from 6 entries. Most of the rest will have used things like support vector machines. Then the next year, these people got the error down to just under 12%. This time, 17 of the 24 entries were deep learning networks. GoogleNet, the next year, got it down to nearly half. And this time, 31 of 32 entries were deep learning networks. Residual learning from Microsoft got the error down to 3.5%. under 3% for this thing in September 2016. A thing called SEs is squeeze and excitation from people in China, and Oxford University got it down to just over 2%. And at this point, it was deemed that the data set used for this challenge was just getting too easy. So they needed to use more difficult training data to, and test data to make the results more meaningful. Anyhow, the latest net is this dense net which came from people at Cornell, Tsinghua and Facebook, January 2018. Yeah, that's the state of the art at the moment. There still is a thing called the labeled faces in the wild data set for specifically for face recognition, which has about 13,000 images of 6,000 people, with about 2,000 of those having multiple images for variations in face pose and lighting and so on. And the error rate or the recognition rate on this now is up to 99.7. It's all getting pretty ridiculous really now. So this is too small to test large-scale recognition. So again, people are moving on to using larger data sets. Facebook of course has a larger data set, but you can't use their data, so tough. So more sets are being built. This, I think, is one of the reasons why Facebook AI research group has now stolen all the best people from the other groups. So there is another data set used by NIST, which is National Institute of Standards and Technology in the US. It's rather small, but it has multiple images of people and videos. So it's generally more difficult. And the scores reflect that. Although having said that, they're getting pretty good already. Vendor test run by NIST was won by NEC from Japan, whose algorithm includes a deep learning and a bunch of other recognition techniques. Deep learning networks are now better than humans under controlled conditions. Humans are still better under really difficult conditions. For example, matching widely different face poses or lighting conditions. Humans are not, however, as good as we think we are. Humans actually make quite a lot of recognition errors. Okay, object recognition. There's a thing called the Common Object, COCO, Common Objects in Context data set, which people like Microsoft actually originated it, and pretty much everyone's now using that. About 330,000 images in there, with about 200,000 of them labeled with whatever's in there. There are about 1.5 million object instances within those. Objects from about 80 categories and general other stuff. Well, I'm not exactly sure what that means, but there are 91 further categories of stuff that aren't actually physical objects. Something like 5 captions maximum per image. And there are also some of people in there with key points annotated. Other recent data sets are these two variants of the so-called Cypher data set, using 10 object categories, and they use rather small images, 32 by 32 pixels. There are 6,000 images for each category. So this is an example of the airplane. There are 10 images from the airplane category. The other version, the Cypher 100, has 100 object categories with fewer images for each category. And it has 2 levels of labeling. Okay. So here's a typical example output. This on this COCO data set. This is from, this group did this real-time object detection with region proposal networks. And this was a deep learning network that really tackled the problem not just of spitting out object labels, but specifying exactly where each object was in the image. And you can see from this result that it's done pretty well on most of the easily locatable and localizable objects. Hasn't been trained probably on this stuff, but otherwise it's done pretty well. Okay, and you get a confidence value for each of these judgments. So why is the performance of deep learning networks so good all of a sudden? Well, it's firstly more complex data models are being learned. Ultimately, all these neural network models are learning a mapping between some input space and some output space of labels and perhaps locations of bounding boxes in images. And you can imagine that the input space of a set of face images, for example, is very large, and the mapping from that onto a large set of labels is a very complex data model. It's a very complex high-dimensional surface, effectively. But more complex data models can be learned with these deeper networks. It's the width of the networks isn't a factor. There's no point having more units than the width of your image, but the number of layers and the number of convolutional layers within each layer that can represent different aspects of the object. The vast increase in that has given much more complex data models. There's more training data, labeled and unlabeled, now available with these big data sets. Large-scale distributed learning is now possible because, well, the internet is just one example, but there are faster networks, networks within computing machinery as well as between them, GPUs, architectures within deep learning machines that connect GPUs together, and it's really all about memory bandwidth to and from your GPU. There are more resources available. IBM and NVIDIA have free cloud and GPU services available for training. Amazon now offer a cloud service where you can train up a deep learning network on Amazon, so you don't have to buy any hardware if you don't want to. I mean, you have to pay Amazon, but you don't, in principle, have to go out and buy GPUs and do all the software. The dropout training algorithm has prevented overfitting, which was an issue for neural networks for quite a while, especially since with a neural network with any number of layers, it's very difficult to know exactly what's being represented by a given unit in a deep layer of that network. So it wasn't always clear when those networks were overfitting. Overfitting still is an issue. You may have seen occasionally there's articles in the newspapers or online about, there was a famous example about a toaster where an object was presented to an object recognition network which was only slightly different from the normal image of that same object, and the output was wildly off. It said that a toaster was a gorilla or something. So that still is an issue, and it's because these more complex data models are now being learned. The problem is you don't know exactly what the shape of the surface is between your training data points. And that goes right back to that example with the trying to fit an m-dimensional polynomial. You don't know, there might be, just going back, all the way back to, where is it? There, right, going back to here. Until a new data point arrives, say here, you don't know that the approximation surface is up here and your network output is going to be way off. So in deep learning networks, that corresponds to the network suddenly making a terrible mistake, even with an input that's quite close to one of the other training inputs. Okay, so overfitting is still an issue. Where were we? Next one. There we go. So overfitting is still an issue. Dropout training does help. There are various versions of this where you miss out training units randomly on some iteration, or you miss out half the data on some iteration or whatever. Open source free software is available for doing all this stuff. All the software that runs on GPUs is open source and freely available. Not all of it, but there is a lot of it available. And there are now all these frameworks available specifically for deep learning. Google's TensorFlow is probably the most well-known one. There are others. Amazon Web Services and Microsoft, etc., use this framework. Here's various. There are loads of them. Increasingly, people are using the Python API, and this stuff continues to evolve at a fairly fast pace. Although I think TensorFlow is pretty much clustered now as the main platform. Okay, main development areas are obviously image, increasingly video recognition. I haven't said anything about networks that use time domain information as well. It's a little beyond the scope of this course, but recognizing objects in videos and actually using the time domain information rather than processing each frame separately is quite a big deal, because you can anticipate that recognizing objects or people in video should be easier than recognizing them in still frames, because you've got this extra dimension, more information in the input signal. So faces, objects, actions, maps, terrain and locations, recognizing road signs for autonomous driving. Video and archive indexing, automatic editing. This is things like producing an automatic summary of a video. Say you've got a half-hour TV program and you want to make a 30-second trailer. There are attempts to do this now with deep learning and other networks. Automatic colorization is an interesting one, which people I work with are doing some work on, because there's still quite a lot of old monochrome black and white video around, or film actually, in archives. And by automatically colorizing that, you can make it appear much less obviously old, and it kind of looks more realistic. The problem with colorizing black and white video, though, or film that's been made into video, is that it's tremendously labor intensive. So if you can do that automatically, that's good. And we have a neural network actually that's just like an object recognition network until the last couple of layers. It's just that the output error measure is a color difference between the color of the training images and the black and white version of the same image. So you can train the network to reduce that instead of spitting out object labels. Okay, self-driving vehicles is obviously a big one at the moment. Pedestrian detection, always a good idea. Detecting other cars and so on visually, although a lot of the communication between vehicles is going to be through other means. Inter-vehicle communication. Industrial and domestic automation for object handling and gripping, navigating around factories, big warehouses like Amazon have got, manufacturing process control. Speech recognition is a big one, and interpretation and synthesis, translation. These are actually very active areas of deep learning research right now. User interfaces, as you will know from voice-activated smartphones and so on. Speaker recognition, obviously, verifying who somebody is one way of doing that, or increasing the performance of face recognition is to couple it with speaker recognition. Games and strategy development. Google has a subsidiary called DeepMind which developed this AlphaGo Zero thing last year, which this is this system was trained up to previously. Okay, the game is called Go, and DeepMind had a system, a deep learning system that learned how to play the game Go. And they used to train this system by effectively inputting historical games that had been played in the past by human masters, Go masters. But they found that if they had the network ignore the human examples and just play the game against itself, it would develop its own strategies which were quite different from the strategies that human masters developed. And this paper from last year, Mastering the Game of Go Without Human Knowledge, was quite a landmark paper. So this is the training time, and the vertical axis here is the number of victories or something. I'm not sure exactly what the measure was, but essentially after this many epochs of training, it superseded this previous version, which had beaten this Go master called Lee, and then after a bit more training, it managed to beat the performance of another version that had beaten this other Go master, and eventually surpassed the performance of any known human master. And that development is still going on there, I think. So that is it. 5 to 6. I thought we were going to be here past 6 o'clock, but I probably went a bit too fast during the early bits of today. Anyway, so does anyone have any questions on anything? If you think of any, you can always ask them next week, but if you've got any now, feel free. Including if there's anything you would like me to explain in more detail, either now or next week,